Alright class, this is the beginning of chapter 3, which is dealing with derivatives. Believe it or not, you guys know what a derivative is. It's another word for doing the difference quotient that we were doing earlier in chapter 2 with limits. Some of the new notation though, f prime of x. So when you take the derivative of f of x, the function is now f prime of x. Okay, we were saying slope before, we were saying rate of change, but this is the notation for the function itself, and it's equal to, again, the limit as h approaches 0 of the function f of x plus h minus f of x all over h. And then again, this only works provided the limit exists, which it usually does for us. So nothing new except for a new word, derivative, and a new notation, f prime of x. So find the derivative, or find f prime of x, when f of x is equal to x cubed. Okay, so we're just going to go through our limit quotient. So I know f prime of x is equal to the limit as h approaches 0 of f of x plus h, which is x plus h cubed, minus f of x, which is x cubed, all over h. You're going to have to do binomial expansion there, or multiply it out 3 times. But as you get cubed things multiple times, you will get better at expanding this. This becomes the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. The x cubes cancel, and so those cancel. Everything else you can cancel an h out, so I have the limit of h approaches 0 of, if the h's cancel out there, we have 3x squared plus 3xh plus h squared. Put a 0 in for h's, and we get that f prime of x is equal to just 3x squared. So the derivative, or the rate of change, is 3x squared. And then again, if you want to know at a point, you could plug in your point at that at this time and figure out what the derivative is at a specific point. However, there is an alternate method of finding a derivative at a point. We kind of did this, but we kind of didn't. It's basically your slope equation, okay? Except for we usually use that with 2 points, but now we're doing it as the limit as the 2 points become 1. So the new alternate definition of derivative that we can use, I want to know the derivative of a point. It's equal to the limit as x approaches that point a, so not 0, and then it's the slope formula. So it's f of x, it's the function minus the function at a over x minus a. So it's very similar to the slope formula, except for the reason why we can use this is that, again, it's the limit as x is approaching a, so they're almost becoming the same point. Again, provided the limit exists. Okay, so let's use this definition to find oh, I messed something up here. Well, I didn't really mess it up. So differentiate this function using the alternate definition, and in this case, we want to say at x equals a. So I needed that part there too. Okay, so we want to find it just at x equals a. So my alternate definition would be f prime of a is equal to f of x, which is square root of x, minus f of a, which is square root of a, all over x minus a. And I forgot a very important part. It's the limit as x goes to a. Well, right now we can't do anything with this limit, because if we plug in a for x, it goes to 0 on the bottom. So we're going to have to manipulate this to make it work. One way to manipulate it, if we have radicals, we can always try to get rid of the radicals and see if something cancels. I know this is kind of, we haven't really done much with this. We usually try to get the radicals off the bottom, but in this case we want them off the top to see what we can do. So one way to do that is to multiply by the conjugate. So square root of x plus square root of a all over the square root of x plus square root of a. And again, the reason why we can do that, or we want to do that, is hopefully you realize that if we do this, we're going to get that out, and then we can cancel it. So I have the limit as x approaches a of, if you FOIL this, we have x minus square root of xa plus square root of xa minus a all over x minus a times square root of x plus square root of a. You don't have to FOIL that one because the whole purpose of this is to cancel out. So we have x minus a on top over x minus a and square root of x plus square root of a. So what happens is we get these cancel. So we get the limit as x approaches a of 1 over the square root of x plus the square root of a. Now we can plug in the limit because this will not make a 0 on the bottom. So we get 1 over 2 square root of a is equal to the derivative at a. Okay, so that is using the new alternate form of the definition of the derivative. Alright, next, notations. So again, things that you will see that all mean the same thing pretty much. Y prime. Okay, again, it's called y prime. That is another way to write f prime of x, which we had earlier up at the top. It just means that you took the derivative of y. So the next one you'll see is dy over dx, and it's called dy dx. And in words, what this means is the derivative of y with respect to x. We did this when we were doing rate of change. Remember the rate of change of a volume with respect to its radius? We did dv over dr. This is saying the function dy is changing with respect to the x value. Another one, it's the same thing. If I have the change in a function with respect to x, we would say that's df dx. And it's the same thing. It's the derivative of f with respect to x. Okay, and then finally we will have something that looks like this, and this basically means take the derivative of f of x. We would say that this is d dx of f at x, and again it's the derivative of f at x. Okay. So those are all the notations. Just copy those down. But they all mean the same thing pretty much. Now here we're going to work graphically with this. Okay, graph the equation, or just graph the derivative from the original function. So this is my original function. I want this to be my derivative. Well, remember, derivative is just the rate of change at a point, or for the function. So we can estimate that, we learned that in the last chapter, by drawing tangent lines and figuring out what their slopes are. So the first and the easiest one to do is, where is the slope 0 for this parabola? Hopefully you realize that the slope of a tangent line is 0 when x equals 2, right? It looks like the slope is 0. So when x is 2, I'm going to put a dot of 0 here, okay? When x is 1, I'm going to say that looks like about -1. And then when x is 0, it looks like it's steeper. Maybe it's a -2. And then when x is 3, now it is a positive. If you draw a line touching just there, that looks like it has a slope of 1. And so on and so forth. And then you should see the pattern. And it's a linear line. It's a line. Linear line seems redundant. It's a line. And what you'll notice as we do these graphs and as we work with derivatives is that with power or polynomial functions, the derivative is always 1 degree less than the one that we took the derivative from. So this is a quadratic, which is an x squared equation. I don't know what the equation is, it doesn't matter, which means that the derivative should look like a straight line that has a slope. Okay? So again, we're graphing the slopes of this graph here. So that means that everywhere when you are to the left of 2, the graph over here has a slope that's negative, which is true. It's below the line here. And then everywhere you go past 2, we have a positive slope, and it gets even more positive. That's what that's saying as you move along the line. Okay. Now we're going to kind of work backwards. Sketch graph of a function that has following properties. Number one, f of 0 equals 0. And number two, the graph of f prime is given below, so this tells us our slopes. And f in part 3, it's continuous for all x, so that means there's no holes in our actual graph. But there's clearly a place where the derivative does not exist, because this is the derivative. So let's look at this. I'm going to just sketch a graph. We know a few things. We know since f prime of x is the slope of f of x, it tells us, this graph tells us that when x is less than 1, the function has a constant slope of -1, and when x is greater than 1, it has a constant slope of 2. And it also tells us, when you see this means we have a point 0, 0. So we have both those pieces. So now I'm going to try to graph this using the information that I know. Okay, so you have to start at the point that is given, which is 0, 0. And we know in this region what is the slope of the line? It's -1, because this is all at -1. So that means that the next point would be here, this point would be here, and so on and so forth. So now what I did was I created a line that has a -1 slope and goes through 0, 0. Okay, now at 1, it changes and the slope jumps up to a line of a slope of 2. So that means after this point I have a slope of 2. So that means that this should be, so this is a slope of -1, this is a slope of 2, and again we know that the graph goes through 0, 0. Sure enough, is there a slope at this point? No, because we're going to call this a corner later, actually probably in a day or two. But because there is a sharp turn, there's no tangent line, there's multiple tangent lines, we don't know what it is, it's not differentiable at that spot. So this is the graph right here, we just did it. Again, just make sure it matches. This gives me a slope of -1, which is good, that's what I need. And I need a slope of 2, that tells me I have that, and it goes through 0. Alright, last thing, this is very quick and easy. Given that the slope at x equals 3, so it says f prime of 3 is equal to -2, and f of 3 is 7. Write equation of a line tangent and normal to the given point. Well, you have to just decipher this. This is one of the easiest problems. It looks confusing, but it's not. This is telling me the slope is equal to -2 when x is equal to 3. Okay? And when x is equal to 3, it also tells us that y is 7. So we have a slope of -2, and we have a point of 3, 7. Okay. So that means for my tangent line, we have the equation x minus the x coordinate. Nope, I'm already doing that wrong. Point slope form starts with y. So y minus 7 is equal to the slope times x minus the x coordinate. And then, so this is for the tangent. And then for the normal, we have to get the perpendicular slope, which in this case is 1/2. So the normal line is y minus 7 is equal to 1/2 x minus 3. Okay, so again, same thing we did in the last section, just with different notation, but it's the same thing. Alright, good job.